So today we will wrap up our discussions on security issues in blockchain. And the topic that we are going to cover today, this is about secure real-time cryptocurrency exchange. And we'll see that how it makes use of certain special hardware security features to have a secure implementation of cryptocurrency exchanges. As we have discussed before, that centralized exchange designs, these are usually found to be vulnerable to theft of funds. These are typically real time in the sense that these cryptocurrency exchanges are similar to stock exchanges and something like your account that you maintain, where you can specify that at what rate you are willing to buy and what rate you are willing to sell, so that if there is a matching seller or a buyer, then the transactions indeed take place in the exchanges uh, for the shares and for other types of commodities. And similarly for uh, these cryptocurrency centralized exchanges, they also support such real-time monitoring of what your different bids are and what others are willing to sell. And this typically that one when one wants to buy something, so it is called a bid, and when one would like to sell something, it's called an ask. So selling is asking for a price and so on. So the decentralized exchanges, which are also possible for cryptocurrencies because they are not vulnerable to theft of funds, but they are not vulnerable because the transactions are indeed actually added to the blocks. And if you are talking about cross currency or cross chain trading, that is from say Bitcoin to Ethereum or Bitcoin to Litecoin and so on, then what we have seen these atomic cross-chain swaps, those examples. But if you want to really go beyond just some simple two-way or three-way such exchanges, where the actual transaction time will be determined by the time it takes to mine those in individual blocks in the respective networks. So you cannot actually carry out real-time trading that you see that the someone is willing to offer at a certain rate. Of course, that is to be published as a transaction, and then you immediately would willing to exchange with that particular offer. So these all will take place only when there is this possibility of uh, doing it real time. But real time such trading cannot be supported in decentralized exchanges, which are always dependent on the transactions being included in blocks. So it is going to be limited by the rate at which the blocks are getting mined in the respective networks. But centralized exchanges actually do not do that. So they maintain some fund and then you carry out the operations, and then they are added to the blockchain. So Tesseract, it is in this context that it is like real time. So it is proposed to be as fast as centralized exchanges, and one can observe the buy and sell prices in real time. And also it allows multiple parties to modify their trading positions in a fraction of a second. So that is what requires to be done when it comes to these types of real-time trading through these exchanges. And also it supports not only for any single one, but that you as if you buy any particular cryptocurrency against some real currency, but also cross-chain asset exchange means one can exchange bitcoins with litecoins and so on. And it is secure against theft by exchange of operators. So it is designed in a way that it satisfies most of the important properties of these uh, real-time exchanges. But how does it do it? It relies on the notion of what is called a trusted execution environment, or T, and the T enables Tesseract to behave like a trusted third party, which controls the funds without exposing them to theft, and at the same time they prevent front running by the exchange operators, which we have seen before. So the reason why we talked about this Tesseract after we completed our discussions on security, and not at the same time we talked about interoperability, is that now you know what is meant by front running. So even if it is through the exchange operators, as we have seen before, so if someone can see things happening in the exchange, that someone is going to buy it in bulk and which is going to raise the price, as we discussed in the context of front running attack. So now the attacker could front run them and put his transactions before that intended purchase that is going to happen, so that one can buy it at a lower price, and in fact, even as we took the example, could sell it back to the intended buyer. So of course, this is something that can be prevented, and also it prevents eclipse attack, as we'll see later on. And finally, it ensures all or nothing settlement, means that either you get the whole thing or not at all. So it is not that it will be partial. So we will touch upon this architecture, which actually what it does is that, say, the exchange, so whatever is the thing like that exchange node, so that will be using there is this technology called Intel's software guard extensions, or SGX. So that is a secure area main processor which is tamper proof, and it guarantees certain things. So which is shown in this diagram here, that there is see, this node, the as such its operating systems and the applications and the exchange, the cryptocurrency exchange application, and that is running, and it can act as a Bitcoin node and maybe another Ethereum node and so on. So these are all in the so-called non-secure world. And then there is the operating systems and then the hardware. Now there is this part of the hardware which is considered to be protected, on which a trusted operating system runs, and on top of it the applications that run are trusted, means that they can be attested by the hardware. So attestation by the hardware means that you get a guarantee that the hardware tells you that this is a version of software that is running and all. So it cannot be a case that some rogue version of software would be running and you will not even know about it. So these are all prevented in the typically this trusted execution environment, which is supported by Intel in the form of SGX, and a lot of work about the architecture of SGX and its functionality, and how it makes that secure environment, and still whether there are some types of attacks possible. So there is a lot of work that have been done. And for this work of Tesseract, which was published in ACM uh, CCS conference in 2019, so that goes by the assumption that this TE is indeed something that is trusted. So that is why the name trusted execution environment. So what it does is that this TEE that guarantees code and data loaded inside it to be protected, and it is guarded against isolation and execution. So it is not affected by execution of the other processes. Integrity of the applications that are running, that is the trusted apps that you see in the diagram. So they have not been tampered with, and also confidentiality of their assets, means the data that is there, that cannot be accessed other than by certain secure means. So these are the ones that are guaranteed by this trusted execution environment. And as I said, that it provides attestation that an output represents the result of such an execution in the T. That means you get some sort of a guarantee that whatever is running in this environment indeed is running in this trusted domain, and whatever are the versions of different software or the applications, that also can are actually returned by this particular hardware. So this, and that is what you call as the remote attestation. That means that this Intel SGX that gives an attestation that this is the version of software that is, for example, running. So any client can actually verify that if I am interacting with this particular software or this version of this exchange, then um, you get that version number, etc., directly from the hardware itself. So we'll see that a strong network adversary can gain complete OS and network control of the host in which the funds are stored, even if this entire node is actually taken over by a very strong adversary. But still, it will not be able to access the information of the data that is stored in this particular SGX, the trusted environment. This is a typical example which shows that so this tesseract design is generic in nature, so it can support a single or multiple such crypto networks. And in this example, we see that it is supporting Bitcoin as well as Litecoin, and we'll see the details later in the steps. But just from the diagram, what it does is like this, that so the effective steps are like this, that there is a primary not the primary, the private key that is generated uh, by this tesseract for each of the networks that it supports. So you have on the left there is this Bitcoin network, and on the right there is the Litecoin network, and there is a private key which is generated by this TEE, the Trusted Execution Environment, for Bitcoin, that is BTC, and maybe another one which is for the Litecoin LTC. So you have these two separate private keys, PKT BTC and then PKT LTC, and these can be generated through double attestation, meaning that these keys can be generated, or one part of the key or one of the keys can be generated by the hardware itself, the trusted hardware itself. So even the exchange operator will not be able to tamper with it. So this can be obtained from the hardware vendor, like Intel will provide that particular key. And so you can have this, so as long as you have trust on the hardware manufacturer and you don't expect it to collude with this administrator, it is fine. But if you do not trust it, that suppose that hardware manufacturer itself is compromising it, that Intel knows it and Intel can set up such rogue exchanges. So that's why you have this double attestation. So you have this private key that is coming from uh, Intel, and also a private key that comes from this reputable um, this exchange operator. So you will be able to work with the two keys together. So there are these types of all guarantees that are provided by Tesseract. So for the timing, for simplicity, we assume that we have this private key which is with key BTC, and the other one is with key LTC. So what happens is that initially that these different users, we will they will keep some money with this exchange, and later on they'll be able to use it. So that is what this is actually trying to depict. So we'll see the steps in the next slide. So I think so you can, I think you can see this part, right, that SIG verify, etc. So this can be verified either by the key of Alice or by the key of the trusted execution environment. So let us see how it works. So we will get back to this diagram once again. So the Tesseract, this is called an enclave, this trusted execution environment that runs in the context of Intel SGX. That's typically denoted as an enclave. So the Tesseract enclave is running some light blockchain clients. So sometimes this is called simplified payment verification clients, or SPVs. So what it does is that how it is guaranteeing certain things. So when this Tesseract is installed, so during initialization, it gets the latest blockchain state. Okay, meaning that it gets the state of, say, Bitcoin. So it knows the latest block in the Bitcoin chain, and it keeps that, and then it generates a key. So of course the secret key and the public key for each supported cryptocurrency. and the enclave will then attest this PK, the public key that is available, as its deposit address for each cryptocurrency. So it will have this PK, which will be the for Bitcoin and one for the Litecoin. And these attested PKs are published through multiple services. So that means the Tesseract exchange is telling me that if you need to make payment to me, you have to make the payment to this public key, and of course that could be a hash of that public key and so on. So this PK forms a depositor address for Tesseract exchange in the corresponding cryptocurrency. So what it means is like this, that the steps are actually fairly simple. Say I would like to join the Tesseract exchange. Okay. So if you see that what we see here, that you see these ads of WazirX and other types of cryptocurrency exchanges, they say that, oh, you can start with as low as say 100 rupees or something. So that is basically your deposit with the exchange. Okay. So similarly here you have to make a deposit with the Tesseract exchange. And how do you make the deposit? You make the deposit by making payment to this Tesseract public key, which has been attested in a particular cryptocurrency. So you can pay, say, 100 Bitcoin to Tesseract's public key in the Bitcoin network. And that is how basically you have opened a Bitcoin account with Tesseract. Similarly, if you want to open a Litecoin account with Tesseract also, so what you will do is that you will pay, say, 1,000 Litecoin in the Litecoin network to Tesseract's this Litecoin public key address, and then that is how the initialization is done. That the exchange has been set up, and then the user has made some amount of deposit with the Tesseract exchange. So that is the first step. So that is what we said. The user opens the account by depositing a significant amount in the deposit address of the exchange, and the proof of deposit is sent to the enclave, so that the enclave can verify the details of this through the transaction and index of the block, Merkle tree, and so on. So that first of all, the exchange should be sure by checking it in the respective chain, so that there should not be a situation that this one does a double spending. So the user should not later be doing a double spending and then getting this transaction made to Tesseract cancelled out. So it will wait for some time, and then it knows that it has indeed deposited irrevocable amount from the user. So it will credit the user's account after verifying the deposit. So now this user account is maintained in the enclave. Okay. So there is this networks, and we have this particular node serving as the exchange, and in the enclave it is now maintaining the user's account. So it also protects against replay attacks by requiring strictly increasing block indices for the user's deposit. So it wants to ensure that same user does not again tell that, oh, see, I deposited 10 bitcoins and now I'm depositing another 10 bitcoins, but it is showing the actually the same details, and in the process trying to replay the earlier details. So those are um, guarded against by following strictly increasing block indices and so on. So now the user's account is identified by the user's public key, and hence the user can use its secret key to generate signed messages to interact with Tesseract. So good thing is that now the interaction between the user and the Tesseract will be through user's public key. Anything that will be digitally signed by the user's public key. So what it means is that the Tesseract will be knowing that indeed it is coming from the real user. So now what happens is that asset exchange, how the asset exchange takes place. So users will post buy or sell orders with their exchange rates. So orders are recorded in the enclave. Okay. So here we see that if we go back now again, that's what I mentioned. So if you see the diagram now, part of it will be clear that here this Alice has already created deposited some amount in Bitcoin network, part of this exchange, and Bob has deposited some amount. Say Bob has deposited 600, and Alice has deposited 5 bitcoins as in their respective networks. So now what we see here is that in this diagram, so Alice is willing Alice has Bitcoin. So Alice is willing to sell her one Bitcoin, but only if she gets a price of 305. Okay, and likewise she is willing to sell 3 bitcoins if she gets a price of 310. That means if someone is willing to pay 305 litecoins, she is willing to buy that and by giving her 1 bitcoin. And likewise, if someone is willing to pay her 310 litecoins for each bitcoin, she is willing to buy those 930 litecoins by exchanging her 3 bitcoins. And similarly, on the right hand side, we see that the Bob, he has deposited 600 litecoins. You see, he has deposited 600, and this Alice has deposited 5 bitcoins, and Bob has deposited 6 bitcoins, as we see here. So now Bob is willing to buy Bitcoin, provided that somebody is willing to sell a Bitcoin up to a price of 299. So if someone is charging more Litecoins, he is not willing to sell those Litecoins, because then it becomes too expensive just for getting 1 Bitcoin. If somebody is asking more, so Bob is not willing to sell his Litecoin. So if you see this is situation now, so these are not matching. So Alice is asking for 305 Litecoins, but Bob is not willing to pay more than 299 Litecoins, and so on. So this is what we mean by the exchange, where we see this in real time, that what are the selling prices, what are the buying prices, and so on. And based on that, if there is a match, then actually the transaction will be carried out by the exchange. So this is what we show mention it here. And then the Tesseract server publishes anonymized version of this order book. So this is order book, means that who is willing to sell what, who is willing to buy what, and it is also again attested by that remote attestation process, as I said. So now you see that what is happening, that real-time trading is executed by matching the buy and sell order. So if these two prices match, so if somebody is willing to buy at 299, then or lower price, then Bob is going to sell his Litecoins, right? And similarly for Alice. So now the important part is that then these exchanges will take place. But the trade, that point number 4 is important, that it does not get reflected in the blockchain networks immediately. Because if that is to be done, that is what we said before, that is what the decentralized exchanges do, that if you want to do it through the networks, through the transactions being mined in blocks, it is going to take some time, so that immediately the order books cannot be updated till the actual blocks are mined. So these exchanges that are happening, these are only reflected in Tesseract exchange sandbox. So it is not actually being written in the blockchain. And also this is something important, because for every such transaction, if you are trying to write it to the blockchain, not only it will have to wait for that to be confirmed, but also it will increase the number of such transactions heavily in the individual network. So what it does is, periodically some settlement transactions are issued by Tesseract in the blockchain network to update users' balances. So from time to time, actually, these users' balances are updated by this. So there were other designs like the Lightning networks and all, which also tried to carry out these micropayments initially and then issue the settlement transactions once in a while. So some of these concepts were there in some of the other exchanges. And of course, the Tesseract, of course, will have to sustain yourself. So it will collect a proportional fee for each successful trade. So something like whatever percentage. So that would help the exchange owners to maintain and upgrade their infrastructure. So that is how asset exchange actually works. Now, finally, that how is it going to protect against different types of attacks? So as we have seen, that first of all, that it is uh, mm, so you might wonder that why, before I come to the Eclipse attack, why front running attack cannot be done. The reason is that the important part is that the communication between the client and the actual TE. This is happening through encrypted messages, which is normally not the case. And because it is not it is encrypted because these keys are known. So between the user and the particular exchange, so all their communications, like who is going to buy, who is going to sell what, these are all encrypted communications. So that is the reason why uh, the exchange itself does not cannot carry out these front running attacks. And even the other aspect is that the transactions are not getting reflected directly in the blockchain, but rather it is taking place once in a while. Now, coming to the Eclipse attack, so resistance against this is important, because if you remember in Eclipse attack, what we said is that the attacker will try to uh, isolate this node from the rest of the network. So, and then it will try to feed these different transactions to this victim node. So, what it does is that uh, if you remember that when we even talked about the attacker for this Eclipse attack, okay, we said that the attacker possibly has 40% computing power, and it is able to separate out the victim with 30% and the rest of the network with 30% computing power, and so on. We had a figure with that. Now, if you see that if this one has less computing power, the attacker, then as it says that it makes an assumption that the adversary controls less than half the computational power. So what will happen is that with not having sufficient computing power, just by separating out this tesseract node itself or the exchange itself, even then this attacker will not be able to mine the blocks at a rate which is the full rate of the entire network. See, if you consider this full network operates at 100% of computing power, considering the aggregated computing power of all the different mining nodes. So if that is the 100%, and with that 100% of computing power of the entire network, based on the current difficulty level, which if you remember is adjusted every 2 weeks or so. So based on that, it is supposed to take about 10 minutes on an average to mine a block. But now, even though this can separate out, then also what will happen is that the attacker is not now able to collude with the other. So attacker has still total 40% capacity of the entire Bitcoin network. So it is likely, so assume that it is less than half the computational power as mentioned here. So what will happen is that even whatever the attacker does, it separates out this tesseract node and all. It cannot generate the new blocks at a rate which is otherwise sustainable by the network itself. So if this 10 minutes is the average time for mining a network, considering the entire computing power of the full network, the attacker is not likely to generate these blocks at a rate any faster than maybe 20 minutes on an average. Okay, so what happens is that based on this, the tesseract node will know that it is being subjected to an eclipse attack, because it will find that it is not getting these incoming nodes generated at the full rate of 10 on an average 10 minutes per node. So, and how does it do it? So it has got a trusted clock. So this, as I said, that it is a trusted hardware with a trusted clock. So one cannot make the clock faster or slower. So the attacker cannot make it faster or slower. Even otherwise, what could have happened was attacker could have taken full control of this node and changed the clock, like the rate at which the clock is getting generated, or tamper with the clock. But this trusted clock is built into the hardware, which can be changed by the attacker. So based on that, since it is running in the enclave itself, which is the trusted hardware component, that it will be able to figure out that it is not getting the new blocks at the rate at which they are supposed to arrive. So with that, it will be able to determine that it is getting the correct the whether it has been subject to eclipse attack, and whether it is now getting this feed of blocks from an attacker. So that can be detected, and it may start ignoring the same. So what happens is that effectively uh, it will be able to detect whether there is any eclipse attack or not. And finally, what is to be kept in mind is that this difficulty parameter, so it starts with the original difficulty level of like the genesis block, or what it can do is that when it is starting, it can get in a secure manner and hard code that current difficulty level of the latest block. So suppose it is currently starting, and say the current difficulty level is say 15 leading zeros, so that 15 leading zeros part will be hard coded, so that it is not fed a block where the attacker will set the difficulty level to be less than those 15 number of leading zeros. Because if attackers had done that and indeed generated the blocks, then checking the or verifying the hashes would have worked correctly. So what is done is that this is hard coded, that what is the current difficulty level to start with, and based on that, as the blocks are mined, and it can keep checking in a secure manner what is the latest difficulty level. So these are the various steps that this tesseract takes in order that it can withstand these types of attacks. And one final point is that here, if you see the script SIG, so what it does is that it says that suppose Alice makes a deposit of say 5 bitcoins, or Bob makes a deposit of 600 Litecoins. These are to be deposited using a transaction which says, so that is, if you see these rounded rectangles on the top left and top right, so what it says is that till you have spent say about 2 weeks, roughly about 2000 blocks or so, which is the rate at which Bitcoin would generate blocks in 2 weeks, or maybe 8,000 if you see in case of Litecoins and so on, that till that time it can only be taken back by this TEBTC, and if it is beyond that, it can be taken back by Alice. So it means that Alice, once has deposited these 5 bitcoins, cannot now take back. So this is that adding those bitcoins to this Tesseract exchange, or these Litecoins to the Tesseract exchange. So once Alice has paid, she cannot take back those, because then there might be these cases, as I said, of double spending and all. So this will be available with the tesseract exchange. So within that, there will be sufficient number of blocks under which it will be buried. So all sorts of such selfish mining attacks and all the other types of attacks that we have talked about, those will not be able to work, because the money will be with tesseract till that time, and tesseract can take those back. The other part is that, you see, the else, so, and if it is greater than that, that means if that amount of time or number of blocks has elapsed, so that is what it says, then it is sig verify pk Alice, or on the other side it is sig verify pk Bob, which means that after that time, whatever is the amount that is there, that can be taken back. But of course, if and this can be done for what reason? This is because if you see that we had this particular attack that was mentioned, that uh, these centralized exchanges are vulnerable to theft of funds. And if you remember, we said that sometimes they shut down and all after they have your money. So what happens is that if that happens, then because this is there in the trusted environment, so after these 2 weeks, if this one even attempts to shut down, this Alice will be able to get back that money, because that transaction was created with this sig verify of PKA or for PKB, where beyond that 2 week time frame, Alice can get back the money. So those are the steps that are taken, so that even if the exchange shuts down, the respective users will not lose their money, which was one of the major concerns of the centralized exchanges. So if we summarize, we see that this Tesseract is trying to address the shortcomings of both the centralized exchanges as well as the decentralized exchanges, trying to ensure that it provides some security, and also at the same time it can support these types of real-time trading, which is by decentralized exchanges otherwise. So this is an interesting work which we wanted to discuss. So this is, of course, the set of papers about front-running attacks and eclipse attacks and selfish mining attack, and the current one, the tesseract, and so on. So you are encouraged to go through these papers also, uh, to to supplement what has been covered in the lectures during the class. So that brings us to the end of our discussion on security in blockchain. So is there any question I can address that? And but otherwise we'll move on to the next topic. So as per our plan, we are now left with some discussions on various applications of blockchain. Professor Chakraborty will start it today. So if there is any question, you may please ask. Also, some of you have been sending some mails that you have some doubts with the assignments from time to time. So please feel free to get in touch with our TAs, and they have been always prompt to help you out. There might be some issues with the mail communication, so if you do not get any reply in maybe a couple of days' time, please feel free to write to them once again, and they indeed would be promptly helping you out.
Excuse me, sir.
Yeah.
Sir, I had a request if you could please explain how this tesseract is secured from the Eclipse attack again, sir.
Oh, sure, sure. See, the Eclipse attack, what it does is that Eclipse attack, first of all, it will try to segregate a particular node. Okay, that is the intended victim. And then what it will do is that it will be feeding its own blocks. But remember that the attacker itself will not have the full mining power of the entire network. It will only have a limited mining power. So even if it is feeding these fake blocks to this particular victim, then it can feed only at a certain rate, and which will be much slower than the rate at which the entire network can generate blocks. So typically, if we consider 10 minutes on an average for generation of blocks in Bitcoin, so in no way the attacker, of course, will be able to generate at that rate. As we said, of course, the assumption is that attacker has less computing power than the entire network's computing power. So remember that when this network is trying to generate it, so everybody is putting in their effort, and we had seen that it is some several hundreds of thousands of terahashes per second for the entire network. So with only that kind of power, the nonce could be cracked. So now what will happen if this particular this tesseract exchange is subjected to eclipse attack, and the attacker, of course, there is no point in simply blocking a particular node, right? It makes sense only if it can be fed with some fake blocks. But the rate at which the attacker can feed those blocks, okay, that cannot be as fast as the average speed of the network. So this Tesseract's trusted environment, that will see that it is getting blocks at a rate which is much slower than the usual rate. So based on that, it detects that it has been subject to eclipse attack. And now, if you see that we see if the attacker knows, sorry, the victim knows that it has been subject to eclipse attack, which we discussed before. That means that it is so essentially its IP, its addresses, its peer network IP addresses, the tables. These have been filled with the attacker's addresses. So if it knows that it has been subjected to it, so it can then actually refresh those tables and start communicating separately and connecting with the other networks. So it can actually flush the entire these peer tables, and then the whatever attacker did was to basically fill the peer tables with its own IP addresses or the junk addresses, as we discussed. So once the victim is aware that it has been subjected, then it will be able to flush those out, and then it will start afresh, and then it will again get filled up with some of the honest nodes. So the attack will get eventually be thwarted. Now, the important part is for the victim to understand at what rate it is getting it, and indeed that because of the trusted talk and also the fact that this difficulty level is indeed available with it, so it can figure out that for the current difficulty level, what is the rate at which it is supposed to get the blocks, and it sees that it is getting the blocks at a much slower rate, and it is because of the trusted clock. That clock itself cannot be changed by the attacker. So in a secure manner, it can determine whether the rate at which it is getting the blocks is much slower than the average rate or not. And based on that, it will then be, if required, it will flush out the peer tables and fill them up again with fresh addresses. So that in that case, attackers' addresses will also go, and some of the honest nodes addresses will get added up. So that is how it will take care of the eclipse.
Roger, sir. So that means that in case if we have an architecture of a trusted clock in any other normal node, then that not if it is not at a safe node, then that node also will be able to detect any kind of eclipse attack on itself.
Yeah. You are absolutely correct. So if anyone can do it, it is good. So the other point that it also is to be done is that it also has to be aware that at what rate. I mean, see these nodes. What they do is that suppose you are running a node, right? So you may not be aware that you have been subject to eclipse attack. So what you will be doing is that you will always be actually getting blocks. You will be verifying the blocks and adding it, right? So it means what? That when you are verifying, you are checking whether the hash based on the block header, if you remember, it will be checking whether it is matching with the current difficulty level and the hash. So the fact that the difficulty level also has been changed or not, that also you have to be careful about. So that's why from time to time it in a secure manner gets the latest this difficulty level and hard codes that in its code, so that any attacker suddenly lowers the uh, difficulty level and keeps pushing in the blocks at the usual rate of say 10 minutes per block, but actually it has reduced the difficulty level so that it can mine the blocks within that 10 minutes. So that also has to be protected against. So these are the two things. One is the trusted clock part, and the other is that it has to get in a secure manner what is the current difficulty level. So from time to time it actually updates that difficulty level. So it is not going to rely on what is written in the difficulty level in the block that has been pushed to it. Yeah, you are right. So it is all about making that part secure.
Thank you, sir.
Okay. So if there is no other question, Professor Chakraborty, you can take over.
Professor Sural, means it is already 12:50.
Mhm.
So, yeah, so I'm guessing that whether it would be a good idea to start it. So,
Okay,
or
I think then, yeah, we'll start next week, next
yeah, so
Wednesday
next
itself.
week we can do a fresh start because
Right,
I
right, right, right.
plan to
That,
discuss about this idea of how to design a blockchain use case.
okay.
So for that, I think it would be better if I can have at least 15-20 minutes.
Okay, I think that is a good idea. So let us then stop here for today. I think we'll start a fresh next Wednesday. And so tomorrow is a holiday, and Friday we'll have that short quiz once again on security topics, as I mentioned in the email, including today's Tessera. And then we'll have the this tutorial followed by assignments by Nisha. And yeah, so that would be a good plan. So let
Okay.
us stop here and wish everybody a very happy Diwali. And we'll meet on Friday for the quiz and tutorial, and next Wednesday for the lecture. Okay.
Sir,
Thank
is
you.
there another assignment?
No, there will not be any other assignment. On Friday, we'll have a tutorial on hyperledger arrays. But on arrays, we will not have any separate assignment. We'll just show you that how you can utilize arrays for identity management.
Yeah, also just to again remind you that so this Friday we'll have a quiz. So that is going to be the fifth quiz, and next Friday we'll have the test, and on the following Thursday, that is on the 18th, right, Professor Chakraborty? 18th
Yeah.
we'll have the final quiz, right?
Yes. Yes.
Because there will be six quizzes, and we'll take the best five out of those six. So this Friday's quiz will be the fifth one, and next week Friday we'll have the test, and following Thursday, we'll have the last quiz based on these topics about applications of blockchain that we'll discuss in between. And no new assignment will be given this Friday. So that is the overall plan.
Yes. Okay. Thank you, everyone. And
No, so just hold on. Yeah, so it is not that. I mean, it is not only the quiz. So it will be quiz followed by that Aries, the tutorial on Aries.
right.
Okay, thank you very much. Bye.
Okay. Take care. Bye bye.
Good Diwali, sir.